Welcome back to another episode of Learning Integration. This episode will be focusing on integration by parts, Lagrange's notation, and trigonometric functions. Now to explain by parts, this is the formula. This is the formula if you do this for a course you will most commonly see. You have similar to how you start off with the product rule. The product rule, you have a function times a function, and because you have a function times a function, you use that and say, well, we need the product rule to solve this. Here we have a function times a function, but because we want to find the antiderivative, we need to antiderive it, and this is what it spits out. Up here you have a function, and on your second function that you're multiplying it to, it's already derived. It's kind of confusing to get your head around, but I'll show you an example because that's the best way to explain this. You got to think of 1 as being normal, the original function. You got to think of 1 as being the derivative of a function. So you start off, let's say we'll have an example. Example 1, we start off with the function h x equals x sine x. Okay. So when you're deducing if you want to use by parts or not, first you got to say, is it a function times a function? Yes. Second, you got to say, can I use substitution? And no, you can't, because substitution implies that the derivative of this will equal something along the lines of this, but the derivative of the x is 1, so it won't find a way. You won't be able to get rid of this x with the derivative of the inside of sine. So substitution's out. And another way, which is sort of optional, is when you derive one of these functions, they'll tend to 0, and that'll be x. I'll show you in a minute. Okay, so let's find the integral of both sides. So if we find the integral of hx, we'll get capital Hx. And if we find the integral of this side, we'll have something that looks a lot like this. So we've found the integral of both sides. We've anti-differentiated both sides. Now, I'll be referring back to this equation. We can say that this here looks very similar to this. We have a function times a function, and we have a function times a function. Now, in order to use this method, we need to assume that one of these is an original function, and one of these is a function that has been derived once, like up here. Now, let's say that we're going to use this, and we're going to use these two as, we're going to pretend that fx is x and g dash of x is sine x. To find the integral, we need to have fx, which we've already got, and we need gx. We've got g dash of x, but we haven't got gx. And also, over this side, we need an f dash of x. We have an fx, but we don't have an f dash of x. So what does that mean? Think of it this way. We have an fx. It's equal to x. We don't have an f dash of x. We need to find that. We have a g dash of x, and we're calling it sine x. We don't have a gx. How would we solve this? Well, if we wanted to find the derivative of fx, we just have to derive fx, which is x. Now, if we derive x, we get 1, and that's what I mean when I said tends to 0. It simplifies down, and it's to 1, so it's perfect. Okay, so we've got that. That's why I didn't choose fx to be sine x, because these can be rearranged to suit how you want it to look, but sine x could have been fx and x could have been g dash of x, but I chose x to be fx and g dash of x to be sine x for this reason, because if we derive x we get 1. We're going to be multiplying something against this later, which is good, because if we're multiplying something against 1, we don't have to worry about it because it's the same thing. So that's why I picked that, because having a 1 in the equation makes things so much easier than having something extra to deal with. But I hope I didn't confuse you. If I did, brush over that, and I'll show you later in the example why. But with g dash of x, it's equal to sine x. Now if we want to find gx, we need to find the integral of sine x. We know that when you derive negative cos x, you get sine x. So if you find the integral of sine x, you get negative cos x. And you could say plus c on the end if you wanted to. That is correct, but because there's a lot of finding the integral all throughout this, you'll be having plus c's, and then you'll be subtracting it, and then you'll be dividing it, and eventually you'll end up with different letters because you want to be technical. So when you're doing by parts, generally you wait till close to the end or the end before you add the c on, and I'll show you that as well. So we have our fx, we have our gx, we have our derivative of fx, and we have our derivative of gx. Now we can fill this in. Okay. I'm going to have to black one of these out. Okay. So we have integral fx, we call that x, and g dash of x was sine x. And that equals fx. Well, we said that fx was x, and gx. We said before that gx was negative cos x, so that's what we're going to write. Negative, we're going to multiply x to negative cos x. Okay, now we're subtracting the integral of f dash of x is 1, and multiplying that to gx. Gx is negative cos x. So 1 times negative cos x is just negative cos x. And then dx on the end. That's why I chose in this stage to derive x, because we get 1. Because it makes it much easier when you get to this bit, because if we had 1 times negative cos x, it'd just be negative cos x. So the less we have to work with, the better. Okay. Now that we've got this, now we've got something to work with. Equals x times negative cos x is just negative x cos x. And here, through multiplication by constants, technically we have a negative 1 times cos x. So, negative 1, if we have a negative 1 times cos x, multiplication by constant means that we bring the constant out the front. If that's the case, we'll have a negative multiplied by a negative 1. 2 negatives make a positive, and we end up with plus. You see how that works? Basically we have a negative, we bring the negative out the front, and we multiply it onto the negative. So we're left with a positive cos x inside, and that's what we have to find the integral of. Okay, now this is the easy part. We just rewrite this out, negative x cos x plus, now here's where you can choose to add the c on or not. First I'm going to find the integral of this. Cos x, when you find the integral of cos, you get sine. And that's what we have. I'm going to add the c in because I choose to add the c into this bit, because at this stage I feel like we're just finding what gx was. We're not really, we're doing the integral to find it, but I don't think of it as finding the integral. I think of it as that's what gx was to begin with. So I don't put the c on there because I don't like carrying the c all the way through. I just like adding the c on here because technically this is correct as well. Now I hope I don't confuse you with that. Try not to worry about that c too much. As long as you have a c at the very end, you should be fine. Okay, so what do we have here? We don't really need these brackets because we're not multiplying anything in. If we were multiplying something into this, then we would need the brackets, but we can get rid of them for now. And it's just linear. It's written linear. So we can just rearrange it. So I'm going to bring the sine x out the front. Minus x cos x plus c. And I only rearrange it like that because it makes it look neater. Because it's better having a positive number out the front than a negative number, if you can avoid it. And so, if I rewrite this down the bottom, the integral of x sine x is equal to sine x minus x cos x plus c. Okay, I'm going to do another example now. Hopefully it'll help sink in a bit more. Okay, example 2. Let's say we have h x equals to x plus 2 multiplied by sec squared x. Okay, like before, we can consider one of these as being fx and the other one being g dash of x. Because this has an x with no power, it's just an x on its own, this here will derive to a 1. So I'm going to choose this to be fx because I already know just by looking at it that it will derive to 1. And this one I will choose to be g dash of x because we know that it's not going to derive to 1 or it's not going to simplify. We're just going to get another trigonometric function out of it. So it doesn't matter if we put it over here because we're going to integrate it anyway. So that's, we've selected what fx is and what g dash of x is. If we rewrite this and we integrate both sides, we get capital Hx, and we get the integral x plus 2 multiplied by sec squared of x dx. Okay, so next step. Now we find we write down what we got and what we need to find. Now, just like before, the formula says we need an fx, we need a gx, we need a derivative of fx, and a gx. Now we know what fx is, and we know what g dash of x is, but we need to know what these three are. Admittedly, two of them are the same, but we need to know what they are. So that's what we're going to find. We've labelled fx as x plus 2. Now we need to find f dash of x. What's f dash of x? Well, the derivative of 2 is nothing, or 0, and the derivative of x is 1. Now, we need to find gx. How do we do that? We find the integral of g dash of x, because we know g dash of x is sec squared x. Sec squared x. Now, you could, because this is essentially sec x to the power of 2, which it is, you could think of it as the power rule or the chain rule or whatnot, or use substitution, but I know, and if you are good with trigonometric functions, or you should know that when you derive tan x, you get sec squared x. So when you integrate sec squared x, you get tan x. Having a textbook or knowing trigonometric functions and their derivatives and their integrals makes things much easier in this process. But if you don't, you can always look it up. Okay, so now we've got this. Let's write out. We're going to put this behind because we're going to rewrite this formula using our new values. Okay, so we have the integral of fx, x plus 2, g dash of x, sec squared of x. Now we know that looks very familiar because that's what we got up top. Now, equals fx, x plus 2 multiplied by gx, tan x. Subtract the integral derivative of fx is 1. Gx is tan x, so tan x multiplied by 1 is just tan x dx. Okay, so now we know this. We can go ahead, now we have the formula written up, we can go ahead and solve it. I'm going to rewrite it back here so I have more room. X plus 2 multiplied by 10, we can just leave it like that. It looks neat enough as is. Okay, now the integral of tan x. Well, the integral of tan x is negative natural log cos x. And then we've got plus c on the very end, plus c. That there in textbook is, in the textbook it says that because that's what it is. When you find the integral of tan x, you get something along like this, negative natural log cos x. Okay, so we have x plus 2 tan multiplied by tan x minus negative ln of whatever. Now we know that we have a minus or a negative times a negative, so that makes it a positive. But we've also got a c down here, and because that's a positive, we get this minus, this subtraction sign, and if we're going to expand it into ln of cos x, we got to expand it into c as well. The only reason I didn't do it for the other question is because it was a positive. We turned it into a positive before this stage. It's still a negative. So if I rewrite this bit out. Okay, now we multiply negative onto a negative. We get a positive ln of cos x. And we multiply the negative onto a positive c. So negative multiplied by a positive is a negative c. Now, you can change that. I like to keep my constants positive at the end. I don't know why, I think that was the way I was taught to do it, but I like having a positive number on the end. So, if you wanted to, just for argument's sake, we'll do it over here. If you wanted to make the letter h equal to negative c, h in this case, in the example we're doing, we don't have a h. H doesn't mean anything. It's just, we can use it as a label for negative c. So if h equals negative c, then we can write all this out. X plus 2 multiplied by tan x plus ln of cos x plus h, and that would equal the exact same thing because we've established that h equals negative c. Make sense? Hopefully it does. So, if I rewrite all this out from start to finish, we get integral of x plus 2 sec squared x dx equals x plus 2 tan x plus ln cos x plus h. And there is our answer. The integral of this is this. I hope you learnt something. Thanks for watching and have a good day.